Hello, calculus students. Let's start this video with a look at the extreme value theorem, which says the following. It says if a function f is continuous on a closed interval, then it has both a maximum and a minimum on the interval. So if you take a look at this example here, so we have a function that has a closed interval. If you look really closely, there's a closed dot here and there's a closed dot here. So this function is closed, and as you take a look at this function, it does have a maximum right here and a minimum right there. So you might want to go ahead and label that. So we have a max right at this point, and this function has a minimum. And that's going to be true for any continuous function on a closed interval. So now let's talk about a function when we're not constrained to a closed interval like we were here. Here we had a closed interval. There were definite endpoints at a and b. So suppose we're looking at a function on an open interval, then that function can have a what we call a relative maximum. I'm just going to abbreviate that max, and a relative minimum that I'm going to abbreviate min, or both on an open interval. These relative extrema, now the word extrema is a plural. The singular form would be extremum, like a maximum is an extremum or a minimum is an extremum. And these relative extrema occur where the graph has a horizontal tangent. A horizontal tangent. If the graph is smooth, Now, if the graph is not smooth, if there's a sharp peak, or if there's a sharp peak or a sharp turn, if an extrema occurs at a sharp turn, then that means that the function is not differentiable at that extremum. So let's take a look at some examples of what we're talking about here. So here's an example of a function that's on an open interval. Now imagine this function could go forever in both directions, but when we're looking in this general area, right at this point we have a relative maximum. Now we know there's a relative maximum there because we could draw a horizontal tangent at that point. Okay, in the second example, here we have a relative min, but notice that's where you have a sharp turn, and that is where this function would be not differentiable. Not differentiable means it doesn't have a derivative at that point. If you think of the limit of the tangent line, the slope of the tangent lines as we approach from the left, it would have some kind of negative slope, and that would be different than as we approach from the right. So at this point, there's no derivative, but you can have a relative min or a relative max at a point where the function is not differentiable. Here's another example of a nice smooth curve, and we have a relative max right here because we could draw a horizontal tangent line, and then we have a horizontal min right here because at that point we could draw a horizontal tangent. Okay, so now let's move on and talk about the definition of a critical number. Okay, so let f be defined at a point C. So we have a function f that's defined at a point C if f prime of C equals 0, or if f is not differentiable at C, then C is what we call a critical number of the function f. Okay, relative extrema, so a relative max or a relative min, only occur at critical numbers. Okay, so here's a couple of examples of what we're talking about. So here we have a relative max. Notice that this is a point where the function is not differentiable. Okay, but it is a maximum, so we would call this C, where that point of that non-differentiable point occurs. We would, at that C, we would say that there is a relative maximum. Here's another relative maximum. Okay, and that means that C is the critical number because that's where that relative maximum occurs. Okay, so let's put this all together and take a look at some examples, like what you'll see in your homework. The directions say we're going to use a candidates test. Use a candidates test to find extrema on a closed interval. So let's say we have a function f of x equals 3x to the fourth minus 4x cubed, and on the closed interval from -1 to 2. So we're going to find the extrema. Now, the extrema can occur at three different places. They can occur at the endpoints. Okay, so when we talk about candidates where extrema could occur, they could happen either at -1 or at 2, or extrema could happen where there's a critical number. So where would there be a critical number? Where the derivative is equal to 0, or where the derivative is undefined. So the first thing we'll need to do is take our function f of x, and we need to find f prime of x. So let's go ahead and find that derivative. The derivative of 3x to the fourth would be bring that 4 around front, multiply it by 3, and then decrease the power by 1. So the derivative of 3x to the fourth would be 12x cubed, and then minus the derivative of 4x to the third would be 12x squared. Okay, now, a critical number would happen where this derivative is either undefined, okay, or where it's equal to 0. Well, I think we can look at this and see it's never going to be undefined. If we're looking for x's where the derivative would be undefined, those would be x's that would make a denominator equal to 0, or would make a radicand less than 0 if we're talking about a square root or some type of even root. So to find critical numbers, we're going to take this derivative and we're going to set it equal to 0. So we'll take 12x cubed minus 12x squared and set that equal to 0. So to solve for 0, let's go ahead and factor out a common factor of 12x squared out of these two terms. So 12x to the third divided by 12x squared would give us x, and then minus 12x squared divided by 12x squared is 1, and that's all equal to 0. So now we'll use our zero product property. If I have two factors that I'm multiplying together and the result is 0, the only way that can happen is if one of those factors is 0. So either this factor, either 12x squared equals 0, which means x would be equal to 0, or the other factor, x minus 1 equals 0, meaning x would be equal to 1. Okay, so now we have found all of our candidates where a relative maximum or a relative minimum could occur. So our candidates are, we have endpoints at -1 and +2. We also have a derivative equal to 0 where there's a horizontal tangent at x equals 0 and x equals 1. So now we're going to make what's called a candidates test. So to make a candidates test, just make a t-chart, make a column for x, and then make a column for f of x. Now we need to go back to the original function, which was 3x to the fourth minus 4x cubed. Then in your first column, go ahead and list all your candidates, and I usually list them from smallest to largest. So of our four possibilities, the smallest is -1, so I'll list that first, -1, and then 0, and then 1, and then 2. Okay, so now what we'll do is we'll evaluate the function at all of those candidates. So when we evaluate f of -1, I'm going to go to my function. Everywhere there's an x, I'm going to put in a -1. So that would be 3 times -1 to the fourth minus 4 times -1 cubed, which is equal to 7. And then when we evaluate f of 0, well, that's just going to be 0 minus 0, which is 0. We'll next evaluate f of +1, which would give us, let's see, 3 minus 4, which is -1. And then last but not least, f of 2, which would be 3 times 2 to the fourth minus 4 times 2 cubed, which turns out to be 16. Okay, so now you just look at your possibilities. Look at your output values. We have a 7, a 0, a -1, and a 16. Well, the smallest of those would be your relative minimum. So here's our relative minimum, and then the largest of those would be your relative max. So when x equals 2, that's where we have a relative maximum. Okay, so to answer our question, find the relative extrema on the closed interval. Let's write our final answer. Let's see where I have space to write it. Let's just say f has a relative max, and we want to tell where that occurs. Well, the relative maximum of 16 occurred when x was equal to 2. So f has a relative max at x equals 2, and f has a relative min at x equals, what was it? X equals +1. Okay, so let's draw a box around that because that's our final answer. And then the last thing I want to do is just take a look at the graph to just verify that. So here's the graph of our function. F of x equals 3x to the fourth minus 4x cubed. So notice here when x is at -1, that's where our relative min of -1 was. And then we had a max at this endpoint where x is 2, our output was equal to 16. So that's our first example of a candidates test. Let's go ahead and take a look at a couple more. Okay, so example 2 says, find the extrema of f of x equals 2x minus 3x to the 2/3 on this closed interval -1, 3. So what we're going to do is find all the candidates and then test those candidates to see which one produces the smallest y value and which produces the largest one. So our candidates are endpoints, so we have two candidates right here, -1 and +3. But to find the other candidates, we need to find the derivative of f of x. So let's take our derivative. So f prime of x would be equal to 2 minus, let's see, if I take 2/3, if I take this 2/3 and multiply it by 3, that would give me 2. Let's see, so we have 2x to the, and then 2/3 minus 1 would give me a -1/3. Okay, so you might want to rewrite that like this: 2 minus 2 over x to the +1/3. So now, that's an exponent. Let me rewrite that so it's a little more obvious that it's x to the 1/3 power. So that would be x to the 1/3. Okay, so now where could extrema occur? Well, they're going to occur where this derivative is either undefined or where it's equal to 0. So, since we have an x in the denominator, we know that this function is undefined when x is equal to 0. That's where we'd have a point where this function is not differentiable. So I'm just going to say undefined at x equals 0. So that's another candidate. The other candidate would happen if anywhere that this derivative would be equal to 0. So let's do a little bit of thinking here. When would this derivative be equal to 0? So I'm going to just take the derivative and set it equal to 0. So that would be 2 minus 2 over x to the 1/3 power. And then I'm going to add that x term to both sides and just write it as 2 over x to the 1/3 is equal to 2. So what x value would make this equation true? Well, if x were equal to 1, the cubed root of 1 is 1, and we'd have 2 over 1 equals 2. So this function would be equal to 0 when x is equal to 1. So that is the x value that would make this derivative equal to 0. So now we have our candidates. Our candidates are, we have the endpoints. Okay, those are two of our candidates where an extrema could occur, or an extremum could occur. We also have x equals 0 where this function is not differentiable. And then we also have x equals 1 where the derivative is equal to 0. So let's go ahead and list those candidates in a table. So we're going to have an x column and then a column for f of x equals 2x minus 3x to the 2/3. All right, so our candidates from smallest to largest are -1, 0, 1, and 3. Now, it doesn't really matter in what order you list the candidates, but I just like to go from smallest to largest. And then let's evaluate at each point. So I'm going to spare you a little bit of the algebra. Well, maybe I better go ahead and do it. So f of -1 would give us -2, and then if I put a -1 in right here, -1 to the 2/3 power would be the cubed root of -1 squared, which is just 1. So this would give us -2 minus 3, which is equal to -5. And then f of 0, that's going to be easy. That's just going to be 0 minus 0, which is 0. And then f of 1 would be 1 minus 1. No, I'm sorry. It wouldn't be 1. It would be 2. If I put a 1 in for x right here, 2 times 1 is 2. Minus, now if I put a 1 in for here, 1 raised to the 2/3 power is 1, and 3 times 1 is 3. So this would just be 2 minus 3, which equals -1. And then f of 3, now this one's going to be kind of funky. F of 3 would be 2 times 3, which is 6, minus 3 times 3 to the 2/3 power. So that's actually going to be 6 minus 3 times the cubed root of 3 squared. So the cubed root of 3 squared is the cubed root of 9. Now, earlier I grabbed a calculator because I need to know about what that's equal to, and that's approximately equal to -0.24. Okay, so now we've evaluated the function in all of our candidates, so let's choose the smallest and the largest. So it looks like we're going to have a minimum here when x equals -1, and a maximum, the max is actually 0 because everything else was negative, so when x equals 0. So you can look at the graph and confirm that. Notice that our minimum occurs right here when x is equal to -1, and then our maximum occurs right here at this point of differentiability when x is equal to 0. So to answer the question, we will say that our function f, okay, f has a relative min at x equals -1, and a relative max at x equals 0. All right, and then let's do one more example together. And this one is going to take us back to your trig days. We're going to have to do a little bit of trigonometry here. So we're going to find the extrema of f of x equals 2 sine x minus cosine 2x over this interval. And this actually has a typo in it, so if you could change this for me. Instead of 0 to pi thirds, I meant that to say 0 to 3 pi over 2. So if you can add a 3 right there. So where can extrema occur? Well, at the critical numbers. Well, either at the endpoints and at the critical numbers. So we know that 0 and 3/2 pi will be two of our candidates. To find the others, let's find the derivative of our function. So if f of x equals 2 sine x minus cosine 2x, then the derivative f prime of x would be equal to, well, the derivative of 2 sine x would be 2 cosine x. So 2 cosine x, and then minus, now when we take the derivative of cosine 2x, we're going to have to use the chain rule because this is the cosine of a function. So take the derivative of the outside. The derivative of the outside function, the derivative of the cosine of something is negative sines of that something. So I'm going to change this negative sign to a plus sign because we're now subtracting a negative. So it'd be a negative sine 2x times the derivative of the inside. Well, the derivative of the inside is 2, so I'm going to put that out front. Okay, so now what we want to know to find our candidates is let's find any critical numbers. So you can notice from the graph, this graph, and we know that sine and cosine curves are nice and smooth. So we're not going to have any points of differentiability. In other words, there's nowhere in this interval from 0 to 3/2 3 pi over 2 where this function is not going to be differentiable. So we don't need to worry about that. What we do need to look for, though, are any x values that make this equal to 0. So let's go ahead and set that derivative equal to 0. So 0 equals 2 cosine x plus 2 sine 2x. Okay, and then we're going to go ahead and rewrite this. Now, this will take you back to your pre-cal days. You might recall a double angle formula. Sine 2x is equal to 2 cosine x sine x. If you know what, that's really hard to read. I'm going to change the color. Let me write that in a different color. Okay, so that double angle formula again is sine 2x equals 2 cosine x sine x. Now, if you don't recall that, don't worry about it. We're just doing this for the, we're going to see a lot of trig in this example, but don't worry about having to do a whole lot in your homework. So what I'm going to do is I'm going to take this sine 2x and I'm going to replace it with this double angle formula. So we'll rewrite this as 0 equals 2 cosine x plus 2 times, well, it'd be 2 times 2, which is 4. So let me erase that 2 and make it 4. So it's going to be 4 cosine x sine x. Okay, so now if you look at our two terms, we have a common factor of 2 cosine x that I'm going to factor out. So let's rewrite that as 0 equals 2 cosine x is our common factor. If I factor it out of the first term, I get 1. If I factor it out of the second term, I get 2 sine x. Okay, so we have this factored. We have two factors multiplied together that equal to 0. So let's set each factor equal to 0. So either 2 cosine x is equal to 0 or 1 plus 2 sine x is equal to 0. 2 cosine, well, we could divide both sides by 2 and just rewrite this as cosine x equals 0. So x, as you recall, would be whatever cosine inverse of 0 is. In other words, what is the angle that gives us a cosine of 0? Now, in our interval, remember we had an interval from 0 to 3 pi over 2. So you might want to think about the unit circle. Okay, on the unit circle between 0 and 3 pi over 2, cosine of 0 would be equal to 0 twice. It would be equal to 0 at pi halves and also at 3 halves pi over 2. So x is equal to pi halves or 3 pi over 2. Okay, let's look at our other factor, set equal to 0. Let's solve that one for x. So I'm going to start by subtracting 1 from both sides. So we'd have 2 sine x is equal to negative 1. I'm going to divide both sides by 2, and we'd have sine x is equal to negative 1/2. So x would be equal to sine inverse of negative 1/2. Okay, in other words, where would we have x values? Where would we have angles that would give us whose sine is negative 1/2? So if you remember, that can only happen in quadrants 3 and 4. So here and here, at this would be 7 pi over 6. Let's see, 7 pi over 6, and over here would be 11 pi over 6. Well, this angle is not even in our. Remember, our range only goes from 0 to 3 pi over 2. So right here at 7 pi 6 is the only place in our interval where we would get a 0 for the derivative. So x is equal to 7 pi over 6. Okay, so now we have all of our candidates. We have the endpoints. We have 0 and we have 3 pi over 2. And then we have our critical numbers, pi halves. Well, 3 pi over 2, we're not going to repeat that. And then 7 pi over 6. Okay, so if we make it a chart now, Let me see where I have a little more space here. So let's make a candidates test chart. So I'm going to have an x value, a column for x's, and a column for f of x. Now I'm going to spare you the trig, and I'm just going to ask you to trust me that when x is 0, f of x, if I plug 0 into our original function, we would get -1. And then our next candidate would be pi halves. If I plug that into f of x, we would get 3. And then our next candidate is 3 pi over 2. And evaluate the function of 3 over 2, we get -1. And then our last candidate was 7 pi over 6. And when we evaluate that, we would end up with -3 halves. Now, to keep this video from getting really long, I'm just going to ask you to trust me with these results. This is way more trig than you'll need to do in your homework, so that's why I'm not going to worry about. If you don't know exactly, or if you don't recall exactly how we got those values, all we did is we took our candidates and we plugged them into our original function right here. And now let's take a look at our table and find our relative max and our relative min. So it looks like we have a relative min at 7 pi over 6. That's where we have the smallest value. And then a relative max at pi halves. So our final answer will look like this. We'll say that f has a relative min at x equals 7 pi over 6 and a relative max at x equals pi halves. All right, so now you've seen some examples and you can get started on your homework. You have 6 problems to do, so give those a shot. And if you have any questions, be sure and ask me when we're in class again.